Welcome to Organic Chemistry. In this video, we tackle the topic of aldehydes and ketones. Let's get started. Aldehydes and ketones both feature carbonyl prominently. Aldehydes are more highly polarized in their pi molecular orbital and less sterically hindered, while ketones have a moderately polar pi molecular orbital and more sterically hindered. Therefore, aldehydes will be the more reactive of the two. We begin with hydrate formation, addition of water to either aldehydes or ketones. This reaction is reversible and equilibrium controlled. We can summarize it as a carbonyl plus water to form a geminal diol. The key thermodynamic idea through all of these is that we're going to replace a pi bond with two sigma bonds. And since sigma bonds are stronger, delta H decreases. But we are going from two molecules to one. Therefore, entropy also decreases. So the hydrate formation is enthalpy favored, but entropy disfavored. We look at the K values at the top, since this is most definitely going to be an equilibrium directed reaction. Electron withdrawing groups, in contrast to what we saw previously with electrophilic aromatic substitution, electron withdrawing groups in this case pull electron density from carbonyl carbons and increase electrophilicity. Therefore, they increase K in this case. And electron donating alkyl groups push electrons towards the carbonyl and decrease electrophilicity, therefore decreasing K. We see that formaldehyde hydrates strongly, while acetone barely hydrates at all. There is also a contrast between base and acid catalysis. Base catalyzed reactions. Hydroxide attacks directly at the carbonyl. This is fast nucleophilic addition. Protonation restores neutrality. For acid catalyzed hydration, we will protonate the carbonyl first and increase electrophilicity, and then water will attack the carbonyl. So acids make the carbonyl more reactive, while base makes the nucleophile stronger. Neither changes equilibrium, only the rate. But now, in the addition of alcohols to form hemiacetals and acetals, we replace water with an alcohol. In our summative reaction, carbonyl with an alcohol forms a hemiacetal. Here we have the same thermodynamics. Sigma bonds are stronger, therefore delta H is favorable. 2 to 1 molecule, therefore delta S is unfavorable. Under basic conditions, alcohols cannot become good leaving groups. We can only form hemiacetals under a basic conditions. We cannot eliminate to form acetals. Why? Because the oxygen bonded to an alkyl group, this is a terrible leaving group unless it is protonated. However, under acidic conditions, now we can protonate the alcohol. And this creates an excellent leaving group, an oxocarbenium ion intermediate, high potential energy intermediate. And this is why acetal formation requires the acid. But because entropy fights us to drive equilibrium forward, we definitely do need to remove water and use excess alcohol. This is why acetals are powerful, however, because we can also use them as an excellent protecting group of carbonyls. They are most definitely stable in bases, even Grignard reagents, and amidst strong nucleophiles. But we can uh, reform the carbonyl by just adding mild acid, and that's synthetic control. But now in the formation of imines and enamines, we swap oxygen nucleophiles for nitrogen. Amines are better nucleophiles. They attack without needing a full carbonyl protonation first. We still, however, need a small amount of acid catalyst. Too much acid, however, an amine becomes protonated and is no longer nucleophilic. Primary amines will form imines. The mechanism functions by nucleophilic attack, proton transfers, the elimination of water, and we form a carbon double bond nitrogen. This is what we call a Schiff base, and this features prominently in many biochemical reactions. Again, removing water drives the equilibrium forward. For secondary amines, we form enamines. There is no nitrogen to hydrogen proton available to eliminate. So depronation must occur at the alpha carbon, and we form a carbon double bond carbon with a single bond to nitrogen. This is an enamine, and this is controlled by sterics and the ability to form conjugation. However, for tertiary amines, there is no nitrogen single bonded to hydrogen, and therefore this cannot proceed. It is fully stopped. In Wolff-Kishner reduction, we weaponize the imine pathway. Hydrazine reacts with carbonyl to form hydrazone. Under a strong base and heat, we eliminate nitrogen gas. And that is absolutely the driving force of this reaction. We go from a hydrazone to an alkane and nitrogen gas. Why is this thermodynamically powerful? Of course, because N2 has an extremely strong triple bond and gas formation increases entropy. This is an irreversible driving force. And this reduction, therefore, removes carbonyl oxygen entirely, leaving the carbon skeleton intact. We use this when there are acid-sensitive substrates, in contrast to the Clemmensen reaction, which we'll review at the end of this video, that requires acidic conditions. But now we turn to hydrolysis and undo everything. These are the reverse reactions of the reactions we have covered so far. The key rule is we use excess water, dilute acid, we remove alcohol or the amine, and we drive reverse equilibrium. For acetal hydrolysis, this requires mild acid, and we protonate the acetal oxygen. Water leaves and the carbonyl reforms. We can also do this with thioacetal hydrolysis, although it's harder. Sulfur stabilizes the positive charge better, and it requires stronger acid, maybe sometimes mercury ion, for assistance. For imine and enamine hydrolysis, we protonate the amine nitrogen. Water attacks, we break the carbon single bond to nitrogen, and we regenerate the carbonyl. This hydrolyzes readily. In enamine hydrolysis, the reverse of formation. We protonate the double bond, water attacks, we reform the carbonyl very much in the similar way as imine hydrolysis. In this, we have built quite a bank of reactions connected to carbonyl chemistry. In the next few slides, we highlight the reactions that we have encountered with oxidation of alcohols to form carbonyls, using acetylides to attack carbonyls, forming uh, alcohols from carbonyls using reduction, using Grignard reagents to attack carbonyls, and finally using Clemmensen reduction to reduce carbonyls to alkanes. And with that, we highlight how these review reactions are definitely stand in contrast to the equilibrium dynamics that we encountered earlier in this video. Aldehydes and ketones feature prominently in biochemistry, and we're going to develop this equilibrium focus in the next few units, going from enols, enolates, and enamines to carboxylic acid derivatives and amines. That is the remaining arc for our year, which has been most definitely excellent. Till next time, Crip.